It is February 18th, 2022. Welcome to the 14th and final lecture in Lattice Boltzmann methods. So today I wanted to do a little bit of repetition and some new things. Maybe it turned out that I get more new things that I actually planned. So we start with we do a case study on a diffusion model, and then we also discuss magic parameters. So we have a target equation. We'll introduce the recursive asymptotic expansion. This is actually something new. Then we look at the target equation for the PDE for the target equation, the PDE for the leading order error, and then we come to this magic parametrization. So 14 lectures, or you have seen 13 lectures. Not all of you have seen all of them, I believe. But the thing that we try to learn here is how to build a Lattice Boltzmann model. And now you should be able, after all of this, you should be able to build a new Lattice Boltzmann model for a new equation. And so we set us this challenge here that you're supposed to derive Lattice Boltzmann model for more or less the simplest equation for which we can derive a model. This is the diffusion equation. So we have a concentration C, and the time, this is changing in time, and this is equal to a diffusion coefficient D times the second derivative, so the Laplacian of C. And now we want to build two different models, so a simple one with one relaxation time and another one with two relaxation times, to see whether we can do actually some magic with this. Okay, so we start off. What is happening here? So we start off in 2 dimensions with our beloved D2Q9 lattice. And now we have to recall, for deriving a model, we have to recall what we learned in lecture 6, the asymptotic expansion. Of lecture 6, and in this it was equation 6.5, which I restate here, and I'll actually give it a new number, namely 14.1, because we are going to use this. So the asymptotic expansion that we had there was the sum over, we need a lot of indices now, M for time, N, and L for space, and Q for the order. This starts from 0 and it goes to infinity, and now here comes this Taylor series expansion in space and time, together with our smallest parameter in diffusive scaling, epsilon by the power of 2m. So this is for time, for space n and L, and for the order, for the asymptotic expansion of the variables, we have to add q here, divided by 2m, by 2 by the power of m plus n plus L. And this goes into the time derivative, the m time derivative, the n derivative in x, and the L derivative in y onto, and you see I'm running out of space, m. So this is what we call the bar moment, the barred moments at the order q, a plus n b plus L, and this into 1 minus 1 n plus L plus m. And by going back in the lecture 6, I noticed that I left out the m here. So Richard Feynman said if an equation is longer than one line, forget it, there will be a mistake. So actually there is a mistake in this, unfortunately. But you know, if you grab the principle of what we are doing, you should be able to derive these things yourself. Always be aware that a lecture like this is not perfect, so there will be mistakes somewhere, and maybe there's a mistake today also. So always try to understand it, and if there's something missing, yeah, you will probably be right by just repairing it and not just believing what I'm saying. So this is the Barth moment, and then we have this omega, which is the collision product, and this is A plus of the moment A plus N B plus L, and this goes into 1 plus minus 1 and N plus L plus M, where M has been missing in the previous version of this equation. So now we have equation 14.1, which hopefully is now the correct one. So just to remind you, this here is the result of this Taylor expansion in space and time of the Lattice Boltzmann equation. So Lattice Boltzmann equation, we write LBE, yeah? Lattice Boltzmann equation, and this Lattice Boltzmann equation is the post-collision state of distribution Fij at position x minus Eij and this delta x half and t minus delta t half minus Fij, this is the pre-collision state, x plus Eij delta x half t plus delta t half equal to 0, where we have this vector Eij just being I and j, and delta t is proportional to delta x square, and this is proportional to epsilon. So epsilon is our smallness parameter, and this is diffusive scaling. So, and now we solve the Lattice Boltzmann equation with a relaxation time approximation, where we usually have several relaxation times, but for simplicity now, to finish within 1.5 hours, yeah, we use the BGK for simplicity, so only one relaxation time. We come to 2 relaxation times later in the lecture. So then we have the moment MAB asterisk. So this is the post-collision state, is MAB plus omega MAB the equilibrium minus the pre-collision version. And this omega AB, this is the post-collision state minus the pre-collision state. So it's more or less the collision operator, if you like. And this now means that we have MAB, which we write as MAB with here the bar. So this is the state in between the pre and the post collision. So I have to subtract half of the collision operator from this state in between to get the pre-collision state, and we have to add half the collision operator to get to the post-collision state. And now this means for the relaxation approximation, so if we put these guys here into this and this guy here into this and this, what we end up with is MAB bar plus omega AB half is equal to MAB bar minus omega AB half plus small omega relaxation frequency MAB equilibrium minus MAB bar plus omega half omega AB half, and this can of course be rewritten as omega AB is equal to omega AB equilibrium minus 1 over omega minus 1/2. So I just noticed that again I have some mistakes in my notes here, but I hope this is now correct. So we write this guy here for simplicity. We write this as tau as equal to omega minus 1/2. So, and you see I'm a little bit lazy today, so I skip all the dimensions of our equation. So we always assume here that delta t is equal to 1 and delta x is equal to 2, because today we have a lot to write. Otherwise I'm getting too much for today. So this here is just to set the stage. So we have the asymptotic expansion and we have the collision operator. Yeah, and now we want to build our model, and for building our model, the first thing that we have to choose is the conserved variables. This is what moment we use for representing our macroscopic variable. So we choose what moment and what order of this moment. And it's asymptotic order. So, and we do this by saying that M00, so the zero order moment, and we take, this is not necessary, but it's allowed, so we take the zero order of the zero order moment and define this as being the C, which is the concentration that we want to solve for. So now, in principle, we have all what we need, but in order to get some new stuff here and getting fancy, I want to mention that there is actually a simplification that we can use. So for deriving the equivalent partial differential equation, which we need, so we are looking for the equivalent partial differential equation of the LBM, which we can, of course, derive using equation 14.1. This can be restated in recursive form. So we'll just, in a minute, we'll see how this is done. One other thing is that we will build the BGK collision into the expansion. So this makes it less general, because you would have to do it in another way if you want to use multiple relaxation times or cumulants. But for simplicity now, we build everything into one equation so that we can actually finish in 1.5 hours with this, hopefully. So, and this is done by replacing MAB, which is of course in our equation 14.1. We replace this with MAB equilibrium minus tau omega AB. Yeah, so this will build in. But first of all, we take a look at the leading order, or the leading term in equation 14.1. So leading with respect to epsilon, of course. So let's just say we go M. So this is our equation 14.1. M N L. Yeah, this is starting. They are starting from 0. And now let's say we are looking at the first term. So we end at 0. Yeah. And say this is M factorial L n factorial L factorial, which of course will all be 1. And this is epsilon M 2m plus n plus L plus Q divided by 2m plus n plus L, which of course all will be now 0. And also all the time derivatives and space derivatives will also all be 0. And here we'll have MQ A plus, what is it, N B plus L. So now I have another possibility to make everything wrong. 1 minus 1 N plus L plus M. And again, all of them are 0. So because all of them are 0 in this sum, because this sum has only one term, this will become 1, and so this will cancel out. And the only thing that is not going to cancel out is this omega n plus n b plus L, and this is again order Q, and this is 1 plus minus 1 by the power of n plus L plus m. Yeah, so we are looking at the first term in this equation, and we see, because this is again, the exponent is becoming 0, so minus 1 by the power of 0 is 1, and so this will be 2, and what we end up here is there's a minus in front of it. It's minus omega AB by the order Q, and this times epsilon Q by the power of Q. So this is the first order term. So the lowest term in this equation. So there's always the collision operator at the lowest term. So if we want to compute the collision operator, and this will be 14.1, what we can do, so take note there's a minus, we could say that omega AB of, say, k now, is omega AB of k, and now comes again the entire equation 14.1, and I remind you that the entire equation 14.1 was set in a way that it is 0. So if we put epsilon by the power of minus k in front of this big sum, m, n, l, and q is equal to 0 to infinity, 1 divided by m factorial, n factorial, l factorial into epsilon by the power of 2, m, n plus l plus q, divided by 2, m plus n plus l. And all of this now goes into the derivatives of t and x and y, and this is applied onto m. Now I introduce the replacement of the collision operator in this stage here. This is then now the equilibrium at the order q, and this is a plus n, b plus l, minus tau omega order q, a plus n, b plus l. So, and this goes again into 1 minus 1 n by the power of n l plus m. And this in addition to omega half by the order q, a plus n, b plus l, into 1 plus minus 1 n plus l plus m, and closing brackets. So what we did is, because this sum already includes this guy here, yeah, what we have is that because there's a minus in this sum, this will cancel out, and what is left will be equal to omega AB at the order k. So now the other thing is that since the equation is not completely done yet, but let me write this down. Since epsilon is larger than 0 and is arbitrary, so we can equate coefficients, and this means that omega AB, yeah, and this must not depend on epsilon. It must not depend on epsilon. We have to restrict, or we can, or we must, I don't know. We can or we must restrict the sum to terms of order epsilon by the power of k. So which means, and this here, maybe I write this in red, that, okay, even though the sum goes from m, n, l, and q from 0 to infinity, however, what we also know is that 2m plus n plus l plus q is equal to k, yeah, because only then will this here cancel with this here. And we get something that is independent of epsilon. So we don't actually have to compute the entire sum. Okay, so this is a good thing. And this means we can call this equation here, which unfortunately has now become very large. So this is now a very practical tool, and this is called the recursive asymptotic expansion. Why is it recursive? Well, we have an equation for omega AB, which of course includes omega AB. So in order to compute omega AB, we have to put it into itself. Yeah. So we have this. Did I give it a name? Yeah, 14.2. So 14.2 is a recursive. This is a recursive equation. So it's recursive because omega depends on omega. So it's on omega A plus N plus B plus L. And this can be computed from equation 14.2 itself. So it's recursive, so does it converge? Yes, it converges, namely then since Q has to be smaller, or it can also be, no, it has to be smaller actually. It has to be smaller than K in 14.2, the recursion is guaranteed to converge. Okay, so and then here this warning, so it's not necessarily easy to use this, so the results of the recursion equation can become very big indeed, and therefore we'll usually use computer algebra. So right after this lecture, there is also the last course of the computer algebra lecture, which of course is the reason why I have to run away in time. And questions have to be answered maybe later offline. Okay, let's do it once by hand. You have to do things by hand at least once in your life. So applying 14.2 to the zero moment. So what is going to happen? So zero moment means we have, so A is equal to 0, B is equal to 0. And K is also equal to 0. Then we have omega 0, 0, 0, which becomes omega 0, 0, 0, which we have in front, and this comes minus what the only thing that the equation delivers is omega 0, 0, and this is 0. So okay, everything is 0. There's no problem with this, but it doesn't tell us anything. Then omega, so k equal to 1, right? So omega 0, 0 to the order not 1, to the order 1 will become omega 0, 0 first order minus omega 0, 0 first order. So this again will vanish, plus dx m10 equilibrium of the order 0 minus tau omega 1, 0 of the order 0, and this plus dy m10 equilibrium order 0 minus tau omega 0, 1 of the order 0. Okay, so this is the first step, and then we do the recursion, because, as I said, we have these guys here, and these are handled with recursion, which I have to write properly. Okay, so we have a recursion number 1. Let me see. So we have omega 1, 0, 0. This is what we want to know, and this is omega 1, 0 of order 0, and this minus omega 1, 0 of order 0. So this is equal to 0. So, and the same thing holds for omega 1, 0, 0, and this is also equal to 0. So there's no information. There's no information in this, so this will just disappear. And we have done the recursion. So let's go back to omega 0, 0 now to the second order. So again, there will be omega 0, 0 to second order minus omega 0, 0 to second order. I stop now writing this because should I? Okay, let's just write it once. So this again will cancel out, and what we are left with is dx m10 equilibrium first order minus tau omega 1, 0 first order plus dy m10 equilibrium first order minus tau omega 0, 1. Now first order, and together with this we have an additional term that comes from the time derivative, which comes one order later because we are in diffusive scaling, and this is m00 equilibrium of order 0 minus tau omega 0, 0, and this of order 0, which we already know that this will disappear. Okay, now again we have these guys here, which we have to, is it the right? No, sorry. So again, we have to do the recursion of this equation. So we have to look into what is omega 1, 0 first order, and this again is of course omega 1, 0 first order minus omega 1, 0 first order plus dx m20 equilibrium to 0 order minus tau omega to 0 order plus dy m yes, dy m11 equilibrium to 0 order minus tau tau omega 11 to 0 order. Okay, and we'll need the other guy too. Omega 011 is omega 01 first order minus omega 01 first order. Should actually stop writing these stupid things here. This is the x derivative m11 equilibrium to a 0 order minus tau omega 11 to 0 order plus dy m02 equilibrium to 0 order minus tau omega 02 to 0 order. Okay, so and the other guys, so omega 00 to 0 order is equal to omega. So to 0 order, these things are, as we've already seen, not making this explicit anymore. These guys are 0. So this means at this point the recursion ends. The recursion has ended and we have converged, actually. So, which means we can combine these and get to equation 14.3, which looks like this, that omega 00 to second order is equal to dx m10 equilibrium first order minus tau dx m20 equilibrium 20 equilibrium plus what did I write here? Right, plus dy m11 equilibrium, so this is of course to 0 order, close brackets, plus dy m01 equilibrium to first order minus tau delta x m11 equilibrium to 0 order plus dy m02 equilibrium to 0 order, closing brackets, and this plus dt m00 equilibrium to 0 order. Okay, now this is the equation that comes out here, and now we have complete control over the equilibrium and we have control over the tau, and with controlling tau and equilibrium we can actually now design our model. So we have to choose now the our moments, and we say that m00 is conserved. So this means m00 equilibrium is equal to m00, and this means that omega 00 at any order is equal to 0. Then in our diffusion equation, we have no first derivative. So we observe here that we get some first derivatives in this equation, but we don't have them in our target equation. So what we do is we simply set these guys that we don't want, we simply set them to 0. Derivatives. So this means that M1, 0 equilibrium and M01 equilibrium, we simply set them to 0 and then we have eliminated them. We also don't have mixed derivatives in our target equation. We have only the derivative in x and the one in y. Second derivatives in x and y. So this guy here, so this would be dx, dy, and this guy here, they would give mixed derivatives. So we don't want to have mixed derivatives. We don't get mixed derivatives if we set this guy to 0. Okay? So this is M11 equilibrium is equal to 0. And now we want to have the correct second derivatives. And this we do by saying that M02 equilibrium should be M20 equilibrium. And this has to be related to C, so we introduce a theta, M00. So usually our theta has always been 1/3. Now we leave it open, yeah, so it could be anything else. So with this, our equation now becomes dt time derivative of M00 to 0 order is equal to dx theta dx tau dx theta M00 to 0 order plus dy tau dy theta M00 to 0 order. And this, of course, now can be written as nabla onto a scalar product tau nabla theta M00. So you see these theta and tau, yeah, they together build our what is this? The diffusion coefficient, but you see they are in different positions in this equation. So theta here is taken the derivative of everything, and tau is in between. So there's nothing in front of this. So this doesn't play any role if tau and theta are constant, as we would usually assume. So but if they are not constant, if they are dependent on space, so then they have, of course, a particular behavior in this derivative. So what we have for tau and theta constant, we can, of course, write that this is dTm00 theta tau. So they are constant. We can put them in front and end up with what we wanted. So then d is equal to theta times tau. So now we are already done, and we have not yet specified our model, yeah, because we still have other moments. What about the moments M21, M12, and M22, which we still have in the D2Q9 lattice? So we see that for the leading equation they have no effect. There's actually no effect, yeah. So we can choose them in any way. We choose, let's choose M12 equilibrium equal to M1 to 1 and 1, 2 being equal to 0. And this M22 equilibrium, so this is an even order moment. I don't like to set this straight to 0 right away, so I set it to gamma M00. So this is leaving this open. So now we wanted to build a BGK model. What we still need for a BGK model is the equilibrium of the distributions, and for this we need the so-called lattice weights. Which now again is supposed to be a repetition. And they come from, lattice weights always come from the equilibrium moments. So we have a system of 9 equations because we have 9 distributions and 9 independent moments. Why is this guy writing the first 9 as a number and the second 9 as a, I'm completely chaotic. Okay, our model moments are defined, so the raw countable moments MAB, they can be calculated from I and j equal from -1 to 1 to I by the power of A and j by the power of B, Fij, under the assumption, which mathematicians don't like, under the assumption that 0 by the order of 0 is defined to be 1. So this is the assumption that you have to make here. So, and now you can compute all the moments in terms of the distributions, and what you can then do is to solve for the distributions. To see how the distributions look like in terms of moments, yeah? And because I don't want to write all of them, I introduce 2 parameters, lambda and small sigma, and they are not equal to 0. And then this distribution f lambda and sigma, so lambda and sigma could be either +1 or -1, yeah. They look like this, so we have 1/4 m11 times lambda times sigma minus lambda m12 minus sigma m12 plus m22. So I'm just using this as a shortcut, so that I have to write, so that I don't need to write all 9 of them, but only 4. So lambda and 0 is 1/2 lambda m10 minus lambda m12 plus m21 minus m22. And of course, f0 sigma is equal to 1/1/2 sigma m01 minus lambda sigma m21 plus m02 minus m22. And this f00, this is m00 minus m02 minus m02. m20 plus m22. So by setting lambda and sigma as 1 and minus 1, so they are element of minus 1 and 1, yeah, you get all the 9 different distributions. Okay, so now, as we said, the lattice weights Wij are distributions at equilibrium and m00 equal to 1. So this looks like the following. So m00 times w11, so if we look at the first equation, at this one, so this is equal to 1 over 4, and lambda is now 1 and sigma is 1, right? So m11 equilibrium minus m12 equilibrium minus m21 equilibrium plus m22 equilibrium. So now, as we've already decided, this guy is 0, this guy is 0, and this guy is 0. So we have not made any decision on this here. So in principle, we could also set this guy to 0 by putting gamma equal to 0. And then we will have the weight w11 is equal to 0. Yeah, and this is funny. So what does it mean? What does this mean in BGK? Well, so this is our D2Q9 lattice. And we are now talking about the guys here in the diagonal, right? So if their omega is equal to 0, what this implies is that we go from this lattice, should make a dot here, so we go from this lattice to this lattice, and this, so it still has 0 velocity, and this lattice is called D2Q5. So we have eliminated for degrees of freedom, so we can use a smaller lattice. Actually, the distributions vanished here. Okay, funny. So we can solve the same equation on a smaller lattice we just learned. So let's look at what is actually W10. W10 in this times M00. This would be 1/2 M10 equilibrium minus M12 equilibrium plus M20 equilibrium minus M22 equilibrium, which gives us 1/2 theta minus gamma, yeah, because we just, this guy gives us theta, and this guy gives us gamma, and this again into M00, so that we can say that omega 110, and this of course is also omega 10. This will also be the other guy, of course. This is 1/2 theta minus gamma 1/2 theta minus gamma. Okay, only one left, namely M00, W00, so the resting channel that we put here in the middle of the lattice. This is M00 minus M02 equilibrium minus M20 equilibrium plus M22, and this is M001 minus 2 theta plus gamma. Okay, so again, we see that we can actually get rid of this, namely when we say, for example, we put gamma equal to 0 and theta equal to 1/2, then this would mean that omega, so we put 1/2, so gamma disappears. 1/2 times 2 is 1, minus 1 minus 1 is 0. So this can be made disappear by putting gamma equal to 0 and theta equal to 1/2, which then means from this lattice D2Q5, we would go to a very simple lattice which has no resting, which has no velocity in the middle, and this is D2Q4. So we can actually solve this diffusion problem with D2Q4, and in that case, our equilibrium distributions, of which we have now only 4, they will all look the same. They will all be 1/4 the concentration C. And then our model just does the following. We have Fij post-collision is equal to Fij pre-collision plus omega Fij equilibrium minus Fij. So, and this is this together with D equal to theta 1 over omega minus 1/2. So this leads to dTc equal to D Laplace C. So this is the solution of our problem. So this was the simple case. Now we have half an hour for the more complicated case. So I think we can do this. There are not too many questions today, because again there are not too many attendees, as I see. So two relaxation time. So this is the second thing. So actually we could have our second challenge. Now we could have, of course, an MRT model where we put one relaxation time for each moment. However, we only have half an hour left, so we'll look at a much simpler problem where we have only 2 relaxation rates, namely one for the odd order moments and one for the even order moments. So assume one relaxation time. So this is tau odd, tau O for odd moments. So the odd moments are M10, M01, M21, and M12. So they are odd. And 1 tau E for even moments. So the zero order moments M 0, 0 is an even moment, but this is not relaxed because it's conserved. So we don't have this one, but we have M02, M20, and we have M22. In principle, we have also M11. Yeah, but this doesn't. Yeah, okay, we have also this one. So with this, our target equation, which is the one that we want to solve, our target equation actually becomes d dt m 0, 0, 0th order, and now this depends only on the odd tau and not on the even tau. So this means that no effect of tau e on the target equation and since it has no effect on the target equation, we of course ask what about the leading error. So we can not only calculate the target equation, but we can also calculate the leading error. And this is again by using equation 14.2. But we do this at a higher order. So previously we had done this for a equals 0, b equals 0, and k equal to 2. And now we do it for k equal to 4. So I don't want to repeat it long again that this kind of model is a symmetric model, and therefore it doesn't has errors of odd order. So we go directly from k equal to 2 to k equal to 4. Of course, we could also prove that k equal to 3 doesn't matter, but we don't have this. We don't have the time left. I see we became more people. This is great. The attendance has doubled. Okay. So this we put into equation 14.2, and because this is now, because Miss k equal to 4, this is going to be very big. I'm already including some assumptions that we know are true. So first we include the assumption of aliasing, which we had in this lecture. So aliasing, I mean M. So we'll have the moment M30, for example, and this would be, for example, go to M10, right? So this is, we build this directly into our expansion. This is one assumption, and we include the conservation, meaning that we know that omega 0, 0 at any order is equal to 0. And then we run the machinery, and here I have to say that this really requires computer algebra, because this is a lengthy calculation. So again, I teach a course in computer algebra that is right after this course. So if you have any questions, you have to write them. You have to write me an email, because later I have to leave to this other lecture. Okay, so using computer algebra, we know that this omega 0, 0 to forced order, we already know it's 0, right? And we can use the computer algebra system to get this solution, so we'll have to compute omega 0, 0. Then we have to apply the recursion to include all the omegas until the recursion has converged. And the result of all of this then looks like this, that we get dt of m0, 0 equilibrium now to a second order minus, so this is a 2, minus tau odd into theta Laplace m0, 0. So I'm already assuming, so I'm simplifying here, I'm already assuming that tau 0 and theta both are not dependent on space. Yeah, so this is my assumption. So this looks familiar because this is a diffusion equation. I've got in here to write this is number to order 2. So I'll give this term a name, namely 1. Now, this is not all of it. We continue with tau odd times tau even into theta plus tau odd square theta minus theta divided by 4. Now, we all depend on that that I did not make any mistakes from copying this. So if I made some mistakes, you have to find out yourself later. So what, okay. By the way, yes, where I just discovered just a short moment, because I just discovered that I actually made a mistake. I'm going to repair this now. This is yes. So I've forgotten. So right. So there's a Laplace operator in front of this. So this is the time derivative of the spatial derivative of m0, 0 equilibrium 0. So I just discovered that I made discovered a mistake in my notes. So I hope there are no further mistakes. So, okay, so this depends. So this is a derivative in space and in time. And this we call term 2. So, and then there is something else which actually looks bigger. Namely, there is tau odd theta divided by 6 minus tau even tau odd square times theta. And this goes into dx x, so fourth derivative, m0, 0 to 0 order, d y, so fourth derivative in y, m0, 0 to 0 order, plus gamma theta 0 minus 6 gamma theta tau even times tau odd square. Okay, so if you want to make sure that all of this is correct, you have to compute it yourself. Maybe I made a mistake, or maybe I made many mistakes, I don't know. But anyway, this here we call term number 3. Okay, so now we identify 3 different terms here, and I will discuss them briefly. So first of all, this what we have here, term 1. This obviously is a diffusion equation. If it was on its own, it would simply be a diffusion equation. For M002, right? So this This is not M000, which we identify with the variable that we want to solve, but with the variable, with the leading error. Yeah, so this is the leading error. This is the leading error of the method. So basically, by having here this partial differential equation of M002, we have a partial differential equation of the leading order error. And this leading order error could, in principle, be 0 for initial and boundary conditions M002 equal to 0. So if we put initial and boundary condition to this guy equal to 0, and we simply solve a diffusion equation. So this diffusion equation with initial condition 0 and would be 0 for all time. So this would disappear, yeah? And this would be good because if it disappears, we have no further error. However, this doesn't work because we also have the other terms, namely 2 and 3. They are source terms in this equation. And they depend on the solution of the target equation. And the solution of the target equation is, of course, not in general 0, because unless we put initial conditions and boundary conditions for this to 0. So this is what it depends on, and this is therefore not 0 in general, and therefore we have, of course, an error in our method. Now these two terms are different. 2 and 3 are different in that way that the term 2 includes a temporal derivative and the terms 3 does not. Yeah, and this is something that we are going to use now. So term 2 includes a time derivative of M00 to the order 0. So this is the solution. The solution of the target equation, and because it's the solution of the target equation, it can be substituted by the target equation. Okay, so this is very important operation that is often used to improve such methods. So what we have here, we have a term that is the time derivative of the Laplacian of the solution of our target equation. And this is the same. So what we can do is we can exchange the order of the differential operator. So we can say this is the Laplacian of the time derivative of the target equation. And what the time derivative of the target equation is, this is something that we know. Namely, this is, so we have to keep this operator. And the time derivative of the target equation is, of course, tau odd times theta times Laplacian of M00. So by using this, so what did we win? The only thing that we won is that we eliminated the time derivative. And so we can put this into now 14.3. Then I recognize I did not specify what 14.3 is, so I have to go back. Sorry for this. So this big equation that we wrote here, this is 14.3. Hope it is 14.3. Maybe, I don't know whether I had. No, it cannot be 14.3. It must be 14.5 already. Sorry, so it must be 14.5. So we put this into 14.5. Okay. Right. So another 15 minutes. So this gives us now equation 14.6, if I'm counting correctly, where we put this, we have put this in. So we have 0 is equal to the time derivative of the leading order error minus tau odd theta Laplacian m00 of the leading order error. So this again is our term number 1, which I have not changed. And now we have replaced the spatial derivatives with the temporal derivatives with spatial derivatives. We've already had spatial derivatives in term number 3, which we can now combine to get tau. So I hope I've done this correctly. Otherwise, we get stuck here. So this is tau odd times theta divided by 6 minus tau even times tau odd square times theta plus tau odd theta square divided by 4 minus tau even tau odd square theta square minus tau odd square theta square. So all of this is getting quite lengthy, is multiplied with dxxxx, so forced derivative m00 of the solution of the target equation plus the forced derivative in y direction of the same guy. So this guy here I call now A. And we get another term that is this is gamma tau odd minus 6 gamma tau even tau odd square plus tau odd theta square half minus 2 tau even tau odd square minus 2 tau odd cube theta square. So okay, the idea is not to torture you with this. So this goes into dxxy m00, and there's no time derivative anymore here because we've combined them into this spatial derivative. So we call this guy here B. So I don't want to torture you with this large terms. So this is more or less is about the idea behind this. So even if this would not be correct, yeah, you just should see the structure of this. So we have this this guy here. This when this would be alone, yeah. So this would allow us to have a zero solution, a null solution. If A and B would disappear. Yeah. So the problem that we have is that we have A and B. Yeah. So this equation, which now is 14.6, would permit so-called null solution. Also, null solution means that this M002 equal to 0 is null. That's M002 equal, so identical to 0, right? If we had simultaneously A equal to 0 and B equal to 0. And this would mean that the leading order error would disappear. So, can we make it disappear? So this, what does it mean? Wait, I have to write it down again. So tau odd times theta divided by 6 minus tau even, tau odd square times theta plus tau odd times theta square divided by 4 minus tau even times tau odd square and this theta square minus tau odd cube theta square. So it would be really a wonder if I didn't miswrite anything here, but just stay with me for the principle. Yeah, don't believe what I'm writing. Just the principle that comes out as the important thing. So the other equation, so this should be 0, and at the same time, gamma tau odd minus 6 gamma tau even tau odd square plus tau odd theta square half minus 2 tau even tau odd square minus 2 tau odd cube theta square is equal to 0. Now we have to solve this. So what do we want to solve it for? So what are our three parameters? In principle, so we have several parameters. Yeah, so we have 6 parameters here. We have 6 parameters, namely, we have theta odd, we have tau odd theta, and we have theta tau even and gamma. So the equation that we want to solve, yeah, so this D is tau odd. Did I say this correctly? Yes. So D is tau odd times theta. So in D is something that we want to adjust. So maybe we would like to keep these guys here open, and therefore we would prefer to solve for these two guys. Okay, so we could also decide differently, but say we keep tau odd and theta and solve for the other guys. And if we do this, is what we get for tau even. We get 2 plus 3 theta minus 12 tau odd square times theta divided by 12 tau, let's write more beautifully, tau odd 1 plus theta, and we get gamma equal to theta 1/3. So this is actually something that I like, because if we derive, so remember gamma, we said that this gamma was defined by in this way, right? So it should be theta. No, it should be the zero moment times gamma is the force moment, and if we derive this from cumulants, we always see that this. So as a side note, so if we derive this from cumulants, we get that gamma should be theta square, yeah? And our theta, usually we prefer to have theta being equal to 1/3. So if we put now theta is equal to 1/3 as an example, so this is just an example, yeah? No, not what I write here, 1/3. Then this would of course mean that we could gamma is equal to 1/9, which is of course theta square. So this would be compatible with what we derive from cumulants. Sarah has a question. No, you stopped writing. No question. Okay, let me continue because we have only 3 minutes left. So in this case, we get TE is 3 minus 4 tau 0 square divided by 16 tau, not 0, tau odd. And since, okay, remember this tau odd is proportional to a diffusion coefficient. So tau odd usually it must be, for stability reasons, much smaller than 1, so that you could say that this is roughly 1/16 tau 0. And this would mean that we can define something that is called theta even odd equal to tau even times tau odd is equal to 3/16. So this is something that in the Lattice Boltzmann world is called the magic parameter, yeah, because a particular behavior of LBM is often, right, nicely, is often seen for a constant lambda even odd. And this is called the magic parameter. And the magic thing here, in this case, is in this case, the magic parametrization leads to a higher asymptotic order. So in this case, this would be forced order. Then expected from the methods. And the good thing with this magic parametrization is it comes at zero cost, because it just has, there are some parameters which are there anyway. So they have no numerical costs. But unfortunately, they can sometimes be unpractical. Impractical. For various reasons. For example, they are not necessarily stable. But whenever they work, so for example, stability, or it has restricted range of transport coefficients. So whenever they work, they make the method, of course, much more efficient. So I run a little bit over time. So this was the last lecture. Yeah, thank you for not leaving me completely alone. If there are any further questions in regards to the homework, then we have to discuss then per email. So please write me an email. We have to stop this because I have a lecture right now. Okay, this.